For this triad, we are going to use coordinate geometry to prove that diagonals of a rectangle are congruent. And they want us to include a diagram with our proof. So we're going to draw 4 points that create a rectangle. And then we're going to connect these points. All right, now I don't like where this point is because it's not on the corner. Okay, so this first point is 0, 0. Then we go to the right, and we're going to go to the right A, but we're not going to go up. Then we're going to go up, but we're not going to go right, and so I'm going to call that distance B, because it's not A, otherwise it would be a square. So we don't go over, but we go up B. Then this fourth point, we went right A and we went up B. We want to prove that the diagonals are congruent. So we want to prove that this line is congruent to this line. And we're going to use the distance formula for that. Remember, the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And we're going to do that twice. So first let's do that for the red line. So from 0, 0 to AB. The x-coordinates are a and 0, so I'm going to use a minus 0, and the y-coordinates are b and 0, so b minus 0. Put those into the distance formula. So parentheses, square them both. Which simplifies to a squared plus b squared, and the square root of that. Now we want to see, and we can't simplify that further, it's just going to stay in variable form. Then we want to see if that's equal to the distance from, on the black line, 0b and a0. So starting with the x-coordinates, I have 0 minus a, and I have b minus 0. So we're going to square these and add them, take the square root. So 0 minus a is negative a, and b minus 0 is b. If I take the negative a and I square it, I get a squared, and I have plus b squared. And that is showing, that's proving that the red line and the black line are congruent, and because we used algebra, this will be true for any rectangle since we used variables, because whatever number you put in for a or b, however big or small your rectangle is, the diagonals will always be congruent. And so we just proved that. Now let's use coordinate proofs to solve problems. An interior designer wants the center of a circular fountain to be equidistant from the sides of a triangular lobby. Where should he place the center of the fountain? So look at this picture. Look at where the center of the fountain is, where they want it to be. And how could we figure out the coordinate of that using algebraic or variable coordinates? Well, let's make a step-by-step plan. We're going to formulate. So fill in these blanks. The center of the fountain must be at the circumcenter of the triangle. Remember, we learned the circumcenter, so that's going to be like when we draw these lines. And where those lines intersect, that's the circumcenter. So we want to find the point of intersection of the perpendicular bisectors of two sides of the triangle, right? We don't have to figure it out for both because all three of those lines intersected at the circumcenter. So let's just use the intersection of the perpendicular bisectors of AC, which is here, and of AB, which is here. An equation of the perpendicular bisector of AC is x equals c over 2. And the reason why that is true is because AC is just a flat line. And when we find the perpendicular bisector of that, right there, it's going to go through perpendicularly at the point c over 2. And when it equals, x equals that, it's just the vertical line. And we know that it's c over 2 because this is c and this is 0, and then 0, 0. And that's how we find the midpoint. And the perpendicular bisector of AB also contains the point a over 2 and b over 2 and has a slope of negative a over b. And the reason why that is true is because we're looking at this line right here, and the midpoint of that is a over 2, b over 2. And it's going this direction. And why is the slope negative a over b? Because you would go down a distance of a and over a distance of b. Then we can plug that into the point slope equation, which you may have learned in Algebra 1, but it's going to be y minus the y coordinate, which is b over 2, is equal to the slope. I'm going to write this just so you guys have it. Point slope is equal to y minus y1 equals m, which is the slope, x minus x1. Just in case you don't remember that from algebra. It's been a while. And then, I'm sorry, the slope would not be m because we're given the slope is negative a over b. And then the point that we're going to put in there is going to be x minus a over 2. Which, if we want to put that into slope-intercept form, it would simplify to equal negative a over b x plus a squared plus b squared over 2b. Next, we have to calculate the intersection of the two lines. So we have two lines. We have this line And we have this line, which was just a vertical line. We want to calculate the intersection. And the way that we're going to do that is we're going to plug in x. So if this equation is x, we're going to plug it into this x because it equals x. So this is quite a bit of algebra. As long as you can follow it, I'm happy with that. I wouldn't ask you to create this on your own without notes. So we're going to plug in to the x, c over 2. And then we have plus a squared plus b squared over 2b. And since we can simplify that by multiplying these two pieces, we would get negative AC over B 2B. And I'm writing it as 2B because the other part of our fraction, this part, is also over 2B. A squared plus B squared is also over 2B. And since they are both over 2B, we can write it as A squared minus AC plus B squared, just putting it all together, over 2B. So what does that mean? That means that the center of the fountain, no matter what the coordinates are of any triangular plaza, if you want to find the center of it, it would be at c over 2, a squared minus ac plus b squared all over 2b. And that completes our notes for 9-2.